In this quiz, we're studying the rate of reactions, and we start with some experimental data, and we're asked in part A to figure out the order of this reaction with respect to the different reactants. And so we have a couple of reactants here, and we need to determine how they affect the rate. And so the first thing we want to do is we want to look at a pair of experiments. So it's 4 experiments for each of these. We have the rate in column 2, write the label in column 1. And then we have the amount of A in column 3 and the amount of B in column 4. And so we want to look at a pair of experiments where one of these stays constant while the other one changes. And we can identify experiment 1 to 2 has the concentration of reactant B that stays constant. And that's great because if we see what changed with reactant A between 1 and 2, which was a tripling, we can determine that the rate change for this reaction is all attributable to reactant A. And in this case, the rate increases 9-fold. What this means is that it's second order with respect to A because a tripling of A causes a 9x increase in a reaction rate, which means that that's a squaring effect. 3 squared equals 9. And this is all attributable to reactant A as reactant B remained the same between these two experiments. Now we need to do the same thing with reactant B, and that will be from looking at experiments 1 to 3, because in this case, A is maintained as constant between 1 and 3, and B increases by a factor of 2. It's double what it was before. When we do that, the reaction rate also doubles, and that means that the reaction is first order with respect to B. This is not the only way that we could solve for this with these specific experiments, and you're definitely open to do things different ways, but it is a solution to how we get the reaction orders for each of these reactants. Now that we have those, we want to state the rate law for this reaction, and this comes in the form of K times the reactants that are raised to certain powers equals the rate. And so in this case, it is as follows. The rate equals K, which is a rate constant yet to be determined, A squared times B. That squared on the A comes from the fact that we've already determined that A is second order and B has a first order power as it is a first order reactant. Now what we want to do is with this data we want to calculate the rate constant including our units. And so we already have our rate law. All we need is our rate constant. And that is as follows. Here is our rate law. To do this, remember that K should be the same no matter what experiment we use. And so we can use whatever experiment we want and get K. They all should agree. They all should lead to K. And in this case, you only need to calculate with 1. They'll all get the same constant. With experiment 2, let's do this first. Our rate is in column 2, and that's 45 moles per liter per minute. And then we get the value of the concentration for A and B. And we solve, and we get that K is equal to 5,000 per molarity per minute. We'll look at those units in a sec. Did want to show that with experiment 4, we can do the exact same thing. We plug in all the data from experiment 4, and yet again, we get 5,000 per molarity squared per minute. How did we get these units? So there's a lot of ways that we can do this. I think right from the rate law is a good way to do this because we see that the rate is moles per liter per minute, that times minute, that's within the denominator. So this is really molarity per minute, and A and B are both in terms of molarity units. We divide and we end up getting molarity to the -2, minutes to the -2, molarity squared and minutes in the denominator equal to K. The final question is saying, well, if we were to multiply the concentration of A by 5 times while also B by 10 times for basically any of these, what change would we expect? So now we want to say, well, how can we predict the change in reaction rate based on the change in our concentrations? And it's important to remember that this is the same rate law and that the effect of each of these will be multiplicative. So both are going to change. We're going to get the effect from both. We can do this algebraically and we say, well, the initial rate is just our rate law. And our second rate is going to be, well, now instead of A, we have 5A. And instead of B, we have 10B. And make sure that the squared applies to the whole thing in the case of the A term. Multiply these out and we get 250. That's our 5 squared times 10. And note that this second half of our right side, rate 2 equals 250 times, is actually the rate law, and that's rate 1. And algebraically, therefore, that shows that these factors multiply, and the second rate after multiplying is 250 times the initial rate. We can also do this more just sort of holistically. We can say, well, second order A times 5 should be a 25-fold increase. That's that squared effect. And first order B times 10 gives us a 10x rate. If we take something and multiply it by 25 and multiply it by 10, that's a 250 multiplied rate compared to what we had before.